This is a video on thin film interference. We'll take a little bit of time to analyze how waves are behaving and why they set up these interference patterns, and then we'll go in and solve some problems on it. To understand thin film interference, we need to remember some things about waves. Waves travel through space and time, carrying energy, not matter. And when we're talking about light waves in thin films, we're talking about a wave train, that is a continuously traveling wave that maintains the same frequency or color as it moves through time and space and different mediums. Now, there'll be a lot of different frequencies, color, wave trains, but it helps to initially think of just one and then scale your thinking. Okay, remember phase. Phase is simply how two waves occupy the space at the same time. Waves can be in phase, crest to crest, trough to trough, and have constructive interference, reinforce each other, or they can be out of phase, crest to trough, and have destructive interference or cancel each other out. When they're out of phase, we say they differ by half a wavelength, or 180 degrees, or pi radians, or some multiple of those. When they're in phase, we say they differ by one wavelength, or 360 degrees, or 2 pi radians, or some whole number multiple of that. In this simulation, I have a green marker and a red marker. They're going to go around in a wheel, and as they turn around, they're going to draw out sine waves individually. Right now, I have them opposite each other, or half a wavelength apart. And I turn it on, and we find that they are indeed half a wavelength apart. Okay, there's a crest for the red sine wave, where the trough for the green sine wave is. So crest and trough are overlapping. That means, of course, there's destructive interference, and indeed the superpositioning over here, both waves combined, gives you 0. So we could say they're half a wavelength apart. We could say they're basically 1 pi radians apart, or 180 degrees out of phase. If I change it so they're in the same location on the wheel, then they are in phase. 0 pi radians phase difference, 0 degrees phase difference, in phase. Now we have crest with crest and trough with trough. And so we have constructive interference, and indeed the superpositioning wave is maximized. So constructive interference means they are in phase. Destructive, totally destructive interference means they're about a half a wavelength out of phase, or 180 degrees out of phase, or pi radians out of phase. Interesting, if I continue to get them out of phase, so they're 360 degrees out of phase, they're back in the same location again. And so 360 degrees out of phase, or 1 wavelength out of phase, is the same as being in phase. So waves are both reflected and transmitted when they hit a boundary or a different medium. The transmitted part maintains the same phase and frequency, but it can change its wavelength as its speed changes. Remember, the speed of a wave depends only on the medium it's traveling through. The reflected part maintains the same frequency, but depending on the boundary, can be shifted in phase. If you have a boundary where you're going from less dense to more dense material, it acts like a fixed end reflection from a rope, and the wave is inverted. Or it has a phase shift of half a wavelength, 180 degrees, or pi radians. If you have the wave going from a more dense to less dense medium, it acts like a free end reflection, in which case the reflected part is not inverted. There is no phase shift. So down below we have some great animations. This is a rope coming off of a fixed end, and over here we have a rope coming off of a free end. And down below we have, going from different mediums, we can see that this transmitted wave, there is no phase shift. That's going from less dense to a more dense medium. Over here on the other side, we're going from more dense to less dense. And again, the transmitted wave, there is no phase shift. Okay, but we go back to this first guy. and look at the reflected wave. The reflected wave, going from less to more dense medium, has a half a wavelength shift. It's inverted, or 180 degrees, or 1 pi radians out of phase. If we go over to the other one, going from a more dense to less dense medium, the reflected wave has no shift. So whether the wave gets shifted or not in its reflection depends on what kind of boundary it's going through. And all of the transmitted waves have no phase shift. So let's take a look at a problem. Jenny and John have set up equipment. They have a 620 nanometer light wave coming into a thin film of oil that is sitting on glass. Light wave coming in. At what thickness of oil would they get maximum constructive interference? So to do this, we have to think about some things. First of all, that transmitted wave, so part of this light wave coming in is going to go into the oil, and that transmitted light wave is not going to have a phase shift. It's going to be in phase. But part of the light is going to be reflected. And when you're reflecting from the air-oil boundary, okay, you're going from a less dense to a more dense medium, and that reflection is going to have a phase shift. It's going to be half a wavelength out of phase. Now, the transmitted part of the wave, the part that's going into the oil down here, it's going to be transmitted a little bit through to the glass, and we're not going to worry about that, but it's also going to get reflected. Okay, that reflected part, it's going from a less dense to more dense also, so it's also going to have a phase shift. So the light coming out of here, eventually going back out into the air, has been phase shifted. How is it going to interfere with itself? So let's do some thinking here. The light coming off of this surface here has a half a wavelength phase shift. The light coming from this surface here also has a half of a wavelength phase shift. So by virtue of the reflection alone, we have a half a wavelength and a half a wavelength, or one wavelength. So if that were the only factor, one wavelength, this would be the reflected light would have crest to crest with the incoming light, and there'd be no problem. But there's an actual thickness here of oil. Not very much, it's a thin film, but there is a thickness there, and that covers a distance, and it takes time to travel through that distance. As the wave is traveling from here back to there, it's also going through its cycle, its sine wave nature. And so as it's transmitted, it goes from crest to trough to crest to trough. And what we want, that as it comes through here and comes back out, how much of a phase shift are we going to have? Well, what do we want? We want for that all of the phase shifts, the phase shift from the first reflection, the phase shift from the second reflection, and the phase shift from it traveling through space and time to all equal a whole wavelength. So we want to equal some whole number times a wavelength. We don't want any halves, because if we have a whole number times a wavelength, then it'll be constructive interference. If we have a half a wavelength, it'll be out of phase as it comes out of the oil, and it'll be destructive interference. And we want maximum constructive interference. So we want this half plus this half plus whatever you lose because of space and time to all equal some whole number multiple of a wavelength. So half of a wavelength from the first reflection plus half of a wavelength from the second reflection plus some quantity has to equal some m number times the wavelength, where m is a whole number. Well, this can't be zero. because we have a thin film there. So the next lowest number it could be that will work for this to be a whole number would be 1, because then we would have a half and a half. This is 1 plus 1, and that would equal 2. So as it travels from the top of the thin film to the bottom and then back up, it can go through one wavelength or one cycle. So it's got to go down and back up. So it can go through one cycle in the down and up. That means each direction it can only go through half of a cycle, right? So this is going to be half a cycle going down, and this is going to be half a cycle coming back up. And half plus half is 1. So how thick is the thin oil going to have to be? Oh, it just has to be half a wavelength. So now we know how thick it is. It just has to be half a wavelength, and we'll have maximum constructive interference. So we want the oil thickness. Oh, that should be easy. Our wave was 620 nanometers coming in. Half of that is 310. But wait a minute. What happens? Remember this wavelength? That's the 620 nanometers. What happens when it gets into oil? It slows down. And when the velocity slows down and the frequency stays the same, V equals lambda F. If V decreases, then and frequency stays the same, the wavelength has to decrease. So we want half of a wavelength. We want half of the wavelength that it is in oil. So we got to figure out what the wavelength in oil is going to be. Okay? And I'm going to go the long route and do it the long way. Okay, we've got a half a wavelength shift from the reflection on the first surface. We got a half a wavelength shift from the reflection on the second surface. And we have a half a wavelength shift as the wave goes towards the back of the oil, and a half a wavelength shift as it comes out. So all total, all the wavelength shifts as the wave comes in and goes out, all of them all together coming out is going to equal some whole number multiple of the wavelength. And the wavelength of this light in air is 620 nanometers. We need to know what the wavelength of this light is in oil. And we have our two old easy formulas, V equals lambda F, and N, the index of refraction, is equal to the speed of light in a vacuum over the speed of light in that medium. So we can do some substituting in here. And we've got C, the speed of light in a vacuum, or in air, is the wavelength of the light in air times the frequency of the light in air. And V, the speed of light in the oil, is equal to the wavelength of the light in the oil times the frequency of the light in the oil. But frequency never changes. So the frequency in air is the same as the frequency in oil, which means we can cancel it out. Yes. And so now we can plug some numbers in here. And we get 1.46, a dimensionless quantity, is equal to 620 nanometers over the wavelength in oil. Or the wavelength in oil is equal to 424.7 nanometers. That's great. But what was the original question? The original question is, what thickness of the oil do we need? And we decided from our reasoning that the thickness would be a half a wavelength, and half of 424.7 is, magically enough, 212.3 nanometers. So our oil thickness should be 212 nanometers. Okay, this is a real nice little simulation. And if we take a look at it, I've got it set up so that we have air in the front, the waves coming in here with air. It's going to a more dense medium, and then there's even more dense medium. Now, in the wave that's being transmitted through all of this, again, there's no phase shift. There is a change in the wavelength because, of course, the speed is changing. But we're not worried about the wave that's being transmitted through. We're worried about what happens when it's reflected, and how does that reflected wave interfere with the wave with itself, with the two waves coming out. So do these guys reinforce each other so you see more coming out? Or do they destroy each other? And right now, the way I have it set up, we have a crest to trough situation. So the wave being reflected from the front of the thin film and the wave being reflected from the back of the thin film are directly interfering with each other. And we've got nothing that you can see. It's destructive interference. If we stop this, if I stop it at just the right point, okay, we can see that this is pretty much 1/4 of a wavelength. Remember, a full wavelength is a complete up and then a down. So we only have part of an up. So we only have 1/4 of a wavelength. So it's got 1/4 of a wavelength to travel to come in. And then there's a phase shift, so it gets inverted. And then we have another 1/4 coming out. But this is a destructive interference, and the problem asks for constructive interference. So instead of having 1/4 of a wavelength, if we shift it so we have 1/2 of a wavelength, okay, now we have a full 1/2 of a wavelength coming in, and then we have a 1/2 of a wavelength coming back out. And we run this, okay, stop it again. Okay, this goes through a 1/2 of a wavelength coming in. It gets inverted on the back side, and coming back out, there's another 1/2 of a wavelength. So 1/2 of a wavelength, inverted, another 1/2 of a wavelength. And then we have the wave being reflected off the front side, and which is inverted also. And so totally, we have one inversion, 1/2 a wavelength, phase shift, 1/2 of wavelength used up in travel, 1/2 and 1/2 is 1, 1/2 of a wavelength, phase shift because it's inverted, and then another 1/2 of a wavelength used to travel. So we have a 1/2, a 1/2, a 1/2, and a 1/2 adds up to 2. Whole number, it's going to be constructive interference. And of course, it is.